Hi everyone. So today I've got a very interesting and special video for you, and I've invited my student who took the exam in IB this year. The reason why I got him here today is his IA is pretty interesting, pretty exceptional, and there's a part called the heat map, which I would like to show you later. And this definitely is something that you want to think about and think about how to create in your IA as well. And this can help you to secure a very good score under personal engagement and also exploration, because well, apparently on the screen here, this is the so-called heat map. And later on, we'll walk you through this. But basically what it does is to show you the error uncertainty as your prediction using your framework. And then you can think about how to set up your experiment, what sort of control variable that you want to choose to be. If you have watched my IE video, there's something that I mentioned before that for control variable, it's not just like, oh, this is control variable, so make it constant. You also can move one more step ahead to choose like what it is, so then the error uncertainty could be minimized. So this eventually will lead you to perform well and ace the personal engagement, because it's involving the design and implementation. And probably the marker will also feel like, oh, you're trying to be very creative and also showing personal significance, as well as under exploration. This will also show that your experiment eventually will have a very good reliability in terms of the design, which means the methodology as well. So this is a part I really appreciate. To be honest, I think my student, by the way, Abraham, okay, is here. Hi, Abraham. Yeah, that this is even too much for a physics IA. I think maybe this is something we should put for physics ED instead. But anyway, he made it here in a physics IA. So without further ado, let me just explain you a bit further on what he did. And then in the next section, he will explain how to achieve this. Basically, it's just use a very simple line of scripts using some codes that you can build it. So first of all, this is his physics IA. Again, I don't expect anyone here to copy everything and also copy the idea. Although I would say the topic, which is the bifilar here, is quite common. This pendulum is quite common. You may find on Google anyway. So this is just an example to show you that how you may do it in a certain topic. And these skills is actually transferable. No matter what topic you're doing for your physics IA, you should be able to do something similar. And like I said, it's going to be good for the personal engagement and exploration. So if you try to search online, eventually you'll find out there's an equation. As every physics IA, like I mentioned in the other IA video, you should know, oh, you should eventually derive, or if you cannot derive, or if you think, oh, I'm not even HL student, I can't really do it, or you can't really find a way to do it very well to derive, but you should still be able to find an equation to describe the dependent variable and independent variable. So in Abraham's case, that would be the big T and the L, which is the length of the phylus, to be the independent variable. And somehow there's a relationship that you can build depending on some other control variable as well, which include obviously the gravitational acceleration, and also R, which something that he defined it as radius of gyration, but it doesn't really matter to you if you're doing another topic. What you need to know is just something that you can choose as a control variable, but you can choose it to be at a different value. So it could be 1, it could be 2, it could be 10, it could be 100. There will be some physical limitation, but at the same time here, we also try to think about and look deeper into the error uncertainty. There's also another control variable which we would not cover in this IA, but then it's also one of them, is the length of the rock itself. So when we try to look at the heat maps here, then you will find out, oh, in terms of different phylus length and also different owl, again, whatever that is, you will find a different combination of it. So instead of just manually calculating it, I'm sure everyone knows how to calculate. Something you learn in chapter 1 with the formula like, oh, delta y over y equals to delta a over a log, and then delta b over b, something like that. I mean, depending on how your framework look like. I mean, you can manually calculate one by one, but that takes ages. So Abraham was smart enough to think about, oh, we can just simply use some programming to figure out for all the scenario that you may have, and then produce this map. So basically, this is what it does. And the good part is not only enable you to do really a good setup for the experiment, you also show to the marker that, oh, the reason I choose the, for example, in this case will be the reason why he choose R to be a certain value at the end. So as you can see here, for different color, it will be representing different percentage error in his own legend, and the blue means vector. So that's why eventually he will be aiming for something like closer to this area. Other than the error itself, he also take this opportunity to show to the marker that, oh, there's also some physical limitation. That's why we did not go further. For example, there's a certain clamp and stand we have in the lab, but I mean, this is have a limited length, of course. So that's why we could not go further in this area. We could not go further in this area. So that's why he drew a line through this and kind of blank out this area on the right. Similarly, there are also some other physical limitation. For example, here, for some reason, he can't go lower than that. So you can see he drew a line, also blank out here. Okay, and maybe for this line, then you can see this is due to a certain literature review. And so if you try to put yourself into the shoes of the exam marker, then you'll find, oh, this is a very comprehensive way to understand why eventually you choose something inside this area because of the physical limitation and also low percentage error. So I think that's pretty much for the basic idea. And in the next part, Abraham will take you to the experience, give you a very simple task, and then you can follow, and then you can see how you can implement this onto your IA. So hi everyone. So we now got Abraham again. Abraham in the screen here. Yeah, so he will show you an example, very simple example using circular motion simply. I'm sure everyone is familiar with that. Again, we are not suggesting doing this for IA. I mean, it's up to you really, but this is just a very simple example to show you how you can, based on this framework, to produce a heat map. And now I'll be his student. So your show time, Abraham.
Okay, so let's say we have a research question, and the research question is to find the relationship between the force of the string and also the radius of the circular motion. So this is our dependent variable, and this is our independent variable. So what our task is to find like which type, like what range of radius or which range of velocities we are going to use in order to minimize the overall percentage error. So let's say that we don't want the percentage error to be like 50% because that would like significantly like reduce the experimental results. Like there'll be a lot of random errors. So we want to make sure it's less than 5%. So what are we going to do is we are going to basically we're going to plot these two values into the x and y axis.
So the x is what? Sorry, the x is
the x. So the x is okay. So the x is basically the radius because we want to find a suitable value for the radius.
The independent variable.
Yeah, it's independent variable. And then the y is also the type of control variable you want. So I'm not sure whether I want the velocity to be 0 or I want the velocity to be 0.5 meters per second. So I'm going to like plot all possible plot all possible values into this heat maps such that it allows me to visualize what percentage error it will be finally generate. Okay, so
sorry to interrupt, but from a physics perspective, we might not be able to control the velocity, but let's just take it this way. Because I guess I don't know what circular motion is, but let's say the usual one that you literally just swing, you know, the whatever object. The velocity is not easy to control. So, but I guess it's fine for our tutorial here. So let's just imagine we can do it.
Yeah. Okay. Yeah. Okay. Assuming we can control the velocity.
But yeah, it's totally fine.
Okay. So the first thing we want to do is basically to identify the equation itself and find the dependent variable and then the independent variable. So we know that the mass, let's say we want to use the mass of 100 grams, which is this one. And then we don't know which velocity of the string, what velocity of the circular motion. So, and also we're going to isolate the independent variable, which is the radius. So, first,
sorry, can I ask a question? So I'm sure some of our audience here may wonder like why we already decide the mass to be 100 grams. So should I ask you here, like you are just trying to provide a random number, really, like 100 gram is like just in case maybe, or someone just using 100 gram slaughter mass to do. And in fact, you can also produce a heat map instead of kind of studying the control variable V. You can also study the control variable of M, mass here. So you can also produce a heat map swapping out the V with the M here. Am I correct?
Yeah. So right now the M is fixed, so we don't have to include that in the axis.
Yeah. So this is just assuming you already have decided what the M is. Yeah. Or should we say in a more even more, I mean, your work is, I guess, is quite sophisticated enough for physics IA. I mean, maybe in a more EE or even university level, we can do a 3D one. Do you think so?
Yeah, I think so.
So the 3D one that can involve then all three things, the M, V, and R that you have. So then you can then project literally a 3D map.
Yeah.
Okay. So I guess for today, let's just keep it simple. Let's just make a 2D first.
Yeah, so the 2D function is basically it takes in two inputs, which is the velocity and then the R. So we want to find like which values are correct. So the function that produces the colors, so the red and the blue colors is given by this function. So it is going to output the percentage error of this function. So let's say we want 0.1 meters per second and 0.1 meters. So it is going to plug it into this function, and then it'll output the percentage error. So to generate this graph. So basically, so the first thing you want to do is to perform the error propagation, which is just with chapter 1's knowledge.
Yeah, basically based on chapter 1 what we learned. And should we add one thing that is here that means you need to know the absolute uncertainty, because on your screen right there on the top right, then 0.01 is the uncertainty for V, and then 0.0005 is the absolute uncertainty for R. So you have to know this first.
Yeah.
Then that's probably is, I mean, again, in different IA will be different, but this may due to maybe the measurement tool. Let's say for R, maybe the ruler itself, the division itself. So this is something that you must know first. Am I right?
Yeah. So
okay.
Yeah. Okay. So now that we know the formula, then we can actually start to generate the code. So, okay, I'm going to exit this presentation first.
Okay, the exciting
So,
part.
yeah, okay, so this is the code for the entire graph generation, and it is written in Python. So I'll assume you know a little bit of Python, but actually you don't really need to know a lot, because you just have to edit one function. So basically this part, you just have to edit this one and then run, like press a few buttons, and then it will work. So, okay, so this notebook will be put in the link in the description, I believe.
Yeah.
And so once you got the link, you just open it into a new tab. Okay. So once you've entered it, it should prompt you to log into a Google account, but don't worry. Yeah. So the first thing you want to do is to run the first cell. So basically, this is one cell of code. So what I'm going to do is just to initialize everything. So I want to initialize the fonts, the graphing libraries, and all those stuff. So
how do
I'm
we
gonna
initialize? Click the button on the
Yep,
left,
so
like the play button.
yeah, this one.
Okay.
Yeah, just the play button. So, and then it will just ask you if you want to run it, but yeah,
Yeah.
it
Because
won't
you are the
access any
author.
data.
You are the author of this, because this file linked to your
Yeah.
GitHub file.
Yeah.
Okay.
So basically now it has already initialized everything like the base code. So now we're going to move on to the second cell. So these are the variables that we want to modify. And this is the function which we want to modify as well. So this function is basically this function. So it takes in two inputs, which is the x-axis, and then it also takes in another function, which is this y-axis. But okay, let's go through each of them, like what each of these things you want to adjust. So basically, the x range is the range of values of x you want to use. So basically, maybe you want to say, I want the velocity to be only between 0 and 0.5 meters per second.
It depends on physically how much you can achieve, right?
Yeah.
So
yeah.
So again, assuming we can adjust the V. So it depends on how fast you can go. So people maybe, some people can go, of course, 0 is okay, but then the other limit could be, in your case, would be 0.5. Maybe some people can go even faster. You can go to say 100, then they can change to 100 here.
Yeah.
Okay.
Yeah, that's basically it. So here, the left one is the lower bound, which is 0 here, and then the upper bound is 0.5.
Yeah.
And it's the same for the y. And then the x divisions, this is just to control the resolution of the heat map. So why we want to do that is because if there's a really complex calculation, then it would take a long time to do so. So what this 100
means, so this is like the
is,
pixel, can I say? The pixel, how many dots? So in theory, up to what I understood, because your division is 100 and 100 for x and y. So in theory, this map already have taken 10,000 calculation, in theory. 10,000 dots basically, and create this map.
Yeah, so basically it iterates through each value. So maybe 0, 0, and then 0.10, and it does that for like 10,000 times. I think.
Very interesting.
If you,
but what if we change the range? Should we change this division also, or it doesn't matter? You can keep it as 100.
Yeah. So actually, I can run the cell first. So I'm going to press this button, and then it should generate a similar graph. So yeah. So let's say you want to change the range to be like 0, 1.
Yeah.
Then it will like it will scale down the graph to like fit your. So basically here.
Okay. So the division actually you can kind of more or less keep it as 100. It will be quite good enough.
Yeah.
Because because it's in a certain trend anyway in physics. So we don't have to go for like 1,000. Otherwise, it will run for a very long time.
Yeah, this is just a a performance tweak. So this cell, it took 4 seconds. So maybe if it takes like over 1 minute, then you might want to decrease it.
Okay.
But yeah, that should be fine. So okay, this one, the X label is basically this one. So
just
actually I can label it first. So in this case, it is so okay, the input of the x-axis is the velocity. So maybe I can like say v velocity. Then the y is the radius, the radius of the motion. So
whatever that is.
R radius. And then the color bar label basically it's the label of the z, so it is the percentage error. So I can say wait, okay, let's go ahead and say percentage error. And this one, the contour line, I'll explain it later. So wait, okay, actually I can explain it now. But okay, so let's say we want to control the percentage error to be less than 5%. So maybe you want to show which regions it is less than 0.5%, like 5%. So here, maybe let's say I want to show the contour lines for 5% error and maybe 10% error.
So you can just add with a comma at the back. So to draw more than one contour line.
Yeah, so this is basically an array, and you can like maybe add multiple values.
Okay, as many as you like.
And then, and if you don't want it, you can just remove everything like this. And then it won't generate. But let's say we want to generate it.
Yeah.
And then you can just press the button.
Yeah. Oh, nice.
Yeah.
Wow.
And then it can show. But yeah, sometimes these lines are not smooth because like this is
division.
The divisions you might have to increase it. But yeah, I don't think this is a huge issue. But
not at all.
Now, for now, I'll just remove this contour line, and then I'll the basic variables are set now. So now all you have to do is just to input this function into it. So okay, I'm going to.
You already done, right?
Yeah, basically it's done, but I can like demonstrate it one more time. So basically it's just delta m. Delta m is 0.001. So and then m naught is basically this.
The value 100 gram. Yeah.
So basically you can just type it like how you normally do on a computer. Like it should like generate the correct one. So
just like decimals, right?
Yeah. So maybe like 2 times this one. So maybe you might want to 2 times a bracket, like to make sure that the order of operations is correct. But okay, so right here, again, this function z is the color. So it outputs the value of the percentage error. So it's going to take in the rate x, the x value, which is the velocity, and then the y value, which is the radius. So right here, delta v is 0.01, which is here. And then v naught is should be the x. So this is the input, which is x. So I can put x here, and then it will basically calculate it for me. And then I'm going to do the same, which is continuous. So plus you add the 0.005 divided by y. Y is the radius. So y. So basically,
that's how you can do it. So if they are doing another topic, then basically, as long as they know physics, how to figure out that error propagation formula, then they just change accordingly here.
So,
okay, that's cool.
Okay, so I think there are some other things, like I think you can use sine or maybe log if you want, like right now it just, I think you can do something like this. I'm not sure if this works, but
Yeah, let's see.
wait.
Oh, so
Oh,
maybe you have to add some library. I'm not sure.
yeah, I think because there's some because like the y it could be 0, so sine 0 is 0, and then
I see,
it throws an error.
How
So
about you change the y range to 0.1, the
yeah,
lower
0.1.
bound? Yeah, let's say, see if it works.
Yeah.
And I guess they will interpret as, oh, it does, it works. But I guess it will take it as what is called radian, right? Instead of degree.
Yeah.
Okay.
Yeah, it
I
should
guess
be
people,
radian.
if you guys really want to, if you have to use trigonometry or log, then you have to check in Python how they define these functions.
Yeah, and
Yeah.
I think there are some like there's some like basic documentation. Wait, if you like, just Google maybe Python log and then sine, and then it will just show you.
Yeah,
So
the
maybe
syntax
like,
is not log but math.log, is it?
yeah, but I
You have
have
to add the library at the top, maybe import math.
yeah, so yeah, I have already imported the math function here.
Oh, it's the,
like
okay.
I've imported all the math functions, so you don't have to press like math.sign.
Okay, just use it.
You just have to sign. So
I see.
like I think there are log. Wait, I think that, like maybe there's a list of functions.
Yeah,
I'm not
sure. Yeah, I'm sure they can find out if they need it.
Yeah, and I think other than log, you can do power as well. So maybe x squared or x to the power of half. You can also do that as well. So I think in my real IA, I use a
Square root.
Yeah, I use square root, and I also use a different error propagation formula. So I use the differentiation that way. So there might be some like higher or like different functions that you can use. So
yeah, but I think that's good enough for our audience here to understand how this can be operated. They don't need to know programming actually. They just have to tweak a few parameters and they can already get a graph. Yeah.
And
how do we save a graph? Is it just right click?
Yeah, so basically it will just output this one. You can either save it or you can go to right here, there's a files button.
Yeah.
And then you can right click it and then download.
Oh, okay.
And then it will just download the JPEG.
That's basically it. Nice.
Yeah. And
anything else?
Not really, but I think you can like modify this graph to like use it for other variables. So again, like maybe you can set the mass to be like set the velocity to be a specific value, and then use the mass as the maybe y-axis.
Yeah.
So you can use that as well.
Right. So this is kind of like a way to get around with not making a 3D one. Of course, 3D one is the most comprehensive and you literally see every dot. So I guess for IA, I as a teacher, I would say what you did with one variable, I think it's certainly very good already. If you really want to, you can just like what Abraham said, try to do another one with the mass, then that will be even better. Or you can still do it, but not include in the report because that will take maybe a bit too long within your page limit. So I guess doing one is very good enough, really.
Yeah.
Okay, so I think that's it for today.
Yep, that is it.
So again, thanks a lot for Abraham sharing this with us. And then I will put your email, should I, or GitHub link?
Yeah, I think if you need more help, like basically in this one, you can contact me on Discord or email. Yeah, that should be fine.
Yeah. So
and like
maybe Abraham is very helpful, and yeah, I'm sure you can ask him for more if you say really have issue with doing other math function and somehow there's an error in the code.
Yeah, and maybe if you like want to edit the like raw code, you can go to my GitHub and then you can download this file and maybe run it on your computer. Or yeah, if you have any issues, feel free to find me. I'm always happy to help.
Okay.
Yeah. Okay.
That's really kind of you. Okay, so once again, thanks Abraham for sharing this with us. I hope everyone, I mean, this is not, I guess, more than just a physics IA. It really is something that a skill that maybe even when you guys move on to university in different discipline, not physics, but maybe engineering or even social science, this may also be something nice to look up with. This actually saves you up so much time. You don't have to, randomly choose a conjure variable, but you now can kind of predict, you kind of foresee what conjure variable would be suitable, would be nice for your experiment, so that you can get the most meaningful result. So thanks Abraham again for joining us today, and we'll see you again next time. So bye.
Bye.